Alright, today we're going to go on to our next unit, which is going to be Chapter 4, and we're going to learn all about the derivative. So, first we're going to look at finding the slope of the tangent line to a curve at a point. This is going to be basically the point of taking a derivative, at least at first. And we're going to use the limit definition of a derivative to find the derivative of a function. So first we need to make sure we understand tangent lines. So you've talked about tangent lines before in geometry, and it might have come up in AATH, I'm not positive. But basically we understand, hopefully, that a line is tangent to a curve at a point P. So if this is what I call P, right there, if the line is perpendicular to the radial line at point P. So this is a circle, so there's the radial line, and this is perpendicular, therefore this line here is tangent. So we want to make sure we understand that when you talk about tangent lines on a circle, the line is never going to cross through the circle. But if we're just talking about a function, the tangent line could still cross the function. So for instance, I have some coordinate plane and some function like this. Well, if I have a tangent line, let's say here, so if I'm tangent right here to the curve, well, I can see that the tangent line still does cross the function at some point. So being tangent to a function does not mean that you don't cross the function. It just means that you're touching the function at one point, at the point of tangency. Alright, so next we're going to talk about the tangent line problem. So this was a problem back in the day on figuring out how can we come up with the tangent line to a function at a given point. And so if we draw a picture, again, so if I have, let's say, some function like this and like this, and if we want to find the tangent line to this function, well, we could first start with a secant line. So if this line is secant to the function, I could find the slope of this line, and I could use that to approximate the tangent line. And the closer and closer these 2 points get to each other, the better that approximation is going to be. So if I label these points, let's call this point here, we'll call that C, comma, f of C, and if we draw this, and I'm going to label this distance right here. This is going to be delta x. The delta stands for the change in x. In that case, then, I know that this point up here is the point C plus delta x, and then f of C plus delta x. So that's this point here and this point here. Now I know, let's see, this segment is f of C plus delta x minus f of C, or I could call that delta y. So now if I want to find the equation of this secant line, I know that the slope of the secant line is y2 minus y1 over x2 minus x1, or delta y over delta x. But if I write that out, that's going to be f of C plus delta x minus f of C all over C plus delta x minus c. That simplifies. Those cancel. And so I end up with a slope of f of c plus delta x minus f of c over delta x. Now you may be realizing, or maybe starting to see the magic that is happening here and what this looks like. And so now again, let's talk about this real quick before we come to the conclusion. And as these 2 points get closer and closer together, this secant line approaches the tangent line. Well, what does that mean that those 2 points are getting closer and closer together? That means that delta x is going to 0. So what does that mean? So as delta x gets small, the secant line approaches the tangent line. So the slope of the tangent line we could write as the limit as delta x goes to 0 of f of c plus delta x, don't worry about that timer, just ignore that, minus f of c over delta x. This is our difference quotient, remember that? Good stuff. We did limits last unit. So now we can find the slope of a tangent line by evaluating the limit of the difference quotient of the function. This leads us to the derivative. So the derivative of a function, this is a major part of calculus, and we'll differentiate until the cows come home. Differentiation. The limit process is used to define the slope of a tangent line. That's what differentiation is for. So it allows us to find the slope of a tangent line. So provided the limit exists, we can say f, this little notation here, we call that prime. So f prime of x, that denotes the first derivative of f of x, is the limit as delta x goes to 0 of f of x plus delta x minus f of x over delta x. Really, it's just a fancy formula for the slope. That's all we're finding is the slope, or the slope of a tangent line to a function at a point. So this is what a derivative is going to give us. Note that it's not going to be a number most of the time. It's going to be another function. And then if we want to evaluate that, or find that tangent line at a given point, then we can plug in values to get an actual number for the slope. So some notation for derivatives. So whether we use y or whether we use f of x or some other function, we'll have this notation here, which I just mentioned on the last slide. So this we say f prime of x. So it's the derivative of f of x. We could also see df dx of x. So this is the derivative of f of x with respect to x. Dy dx is the change in y with respect to x. Capital D of f of x, so that's the derivative of f of x. Or you could just see y prime. So all of these are just different notations for derivative with respect to x. If the limit exists at x, then we say f is differentiable at x. Okay, let's do an example. So find the slope of the graph of f of x equals 2x plus 1 at the point 2, 5. So we know that the derivative is the limit as delta x goes to 0 of f of x plus delta x minus f of x over delta x. So that means we just need to evaluate this limit when f of x is 2x plus 1. So this is going to be the limit as delta x goes to 0 of 2 times x plus delta x plus 1 minus 2x minus 1 over delta x. So this was, that right there is the f of x. This is the f of x plus delta x. I've distributed the negative already. So now we evaluate the limit. We need to simplify. So the limit as delta x goes to 0 of 2x plus 2 delta x plus 1 minus 2x minus 1 for delta x, the 1, the 1, the 2x, the 2x all go away, and we get the limit delta x goes to 0 of 2 delta x over delta x. Those go away, so we get 2. So that is the slope. So we want to find the slope of the graph of f of x equals 2x plus 1 at the point 2, 5. Now here in this case, the derivative is 2 no matter where we are. So the slope is going to always be 2. Had this come out to be a separate function with an x in it, then we would plug in the point. Now, I did this example because we should have known this from the beginning. What is this the equation of? Well, this is the equation of a line. We know that the slope of a line is constant the entire time. F of x equals 2x plus 1. It has a slope of 2. Therefore, any line that is tangent to this line at any point is also going to have a slope of 2. Okay, so now, what if it's a nonlinear function? So I want you to try and find an equation of the tangent line at x equals 1 and at x equals negative 2 of f of x equals x squared plus 3. So pause the video, unpause when you're ready to check your work. Alright, so first thing I did is over here off to the right is I found what is f of 1 and what is f of negative 2, because I'm going to want the point 1, 4 in this case and negative 2, 7 to help me find the equation of a line. Alright, so then once I found that, now I went through the limit, or the derivative process. So the limit is delta x goes to 0 of x plus delta x quantity squared plus 3 minus the quantity x squared plus 3 all over delta x. One thing to point out, there is a shortcut for this. Maybe if you have some friends in calculus, they have already told you the shortcut. We will learn the shortcut. Once you learn the shortcut, you're going to be pissed that you had to learn this long definition or limit definition version. However, there is still importance to this, so this is what we're going to do for now. So this is the amount of work that I expect to see on our 4.1 quiz. So make sure you pay attention to the amount of work I'm writing here, as well as the organization of the work. Notice that I'm also writing the limit as delta x goes to 0 every time. It's important that you write that step. Okay, so then I multiplied out x plus delta x squared, distributed the negative. Remember that when we do the difference quotient, everything without a delta x in this case should cancel. So the x squared, the negative x squared, the 3, and the negative 3. Now I can factor out a delta x in the numerator, and it reduces with the delta x in the denominator. Therefore, the limit as delta x goes to 0 of 2x plus delta x is going to just be 2x, because the delta x is 0. So now I can do my direct substitution. So the derivative of f of x, f prime of x, is 2x. Therefore, f prime of 1 is 2. So the slope at the point 1, 4 is 2. The slope at negative 2 is negative 4. So now I can write the equation of a line in point-slope form. Most of the time this is going to be easier than slope-intercept form. And I have y minus 4 equals 2 times the quantity x minus 1, and y minus 7 equals negative 4 times the quantity x plus 2. Alright, we're going to end part 1 here. There are a few more examples that I want to do, so that'll be on part 2. This is the end of part 1.